Hi everybody, welcome back. I just want to finish up section 14.6 on tangent planes and differentials with a couple of quick examples on applications of differentials, what these differentials can be used to estimate. And they can be used to estimate error in measurements or amount of material used in constructing an object, in particular hollow objects or objects that are very thin, like a metal can or something like that. So really all I have for you are two examples. The first one deals with a measurement and a tool that's used to measure something, and there might be some error in that tool. So it says the error in measuring each dimension of a box is plus or minus 0.1 millimeter. If you have a box with dimensions 50 by 20 by 15 centimeters, find the maximum error in calculating the volume of the box. So if we have some measurements, 50, 20, 15 are the measurements. Each of these measurements might be off by plus or minus 0.1 millimeters. So if this is the case, what's the maximum error we could have in the volume? So before we get started, let's see what we're dealing with. Volume of a box, length times width times height. Now, in the problem, it doesn't tell us which measurement represents length, width, or height, so let's just say that length is 50 centimeters, width is 20 centimeters, height is 15 centimeters. We need to determine what to do with this plus or minus 0.1. Are some of the measurements positive or some of the measurements negative? Well, if we want the maximum error in calculating the volume, then we want all of these to either be all over measuring or all under measuring. In other words, I want to take the error in all three directions as either 0.1 or all three is negative 0.1. That's going to give us the maximum error. If I take combinations of positive 0.1 or negative 0.1, the error is not going to be as much. It could be different. So I'm just going to take them all to be positive, say that we're over measuring all of these. So DL, DW, and DH are all 0.1 millimeters. And here we need to change our units, right? If we're measuring length, width, and height in centimeters, and the error is in millimeters, I want everything to be in centimeters, because in the end I'm going to be taking a measure of volume. And I want my volume to be in cubic centimeters. I don't want my volume to be in square centimeters times millimeters. That's a weird unit of volume. So we convert 0.1 millimeters to 0.01 centimeters. And now we can look at the equation for the differential. The volume is a function of three variables. So I'm going to have three terms in my differential. The partial derivative of v with respect to L, dl, plus the partial derivative of v with respect to W, dw, plus the partial derivative of v with respect to H, dh. Now I actually have to take these partial derivatives, but the equation formula for volume is pretty simple, right? So these partial derivatives, with respect to L I get W times H, with respect to W I get L times H, and with respect to H I get L times W. And now the formula for my differential is as written there. It's W times H times dl plus L times H times dw plus L times W times dh. And now I have all the information I need. I could just plug in numbers and see what I get. So everywhere I see a W, I'm going to plug in 20, so I get 20 here, 20 there. Everywhere I see H, I plug in 15. And everywhere I see L, I plug in 50. And DL, DW, and DH are all 0.01. So then 20 times 15 is 300. I just move the decimal place back 2 spaces. 50 times 15 is 750. Move the decimal back 2 places. 50 times 20 is 1,000. Move the decimal place back 2 places. That's multiplying by 0.01. Add them together, I get 20.5 cubic centimeters. So the maximum error in calculating the volume of the box is 20.5 cubic centimeters. Now, is that large? Is that small? To give some context, right, I have a ruler. Going old school technology here. So 3 centimeters is this much. Why am I talking about 3 centimeters? Well, if I take a box that's 3 centimeters on each side, So 3 centimeters by 3 centimeters by 3 centimeters. So you can use your imagination from there, how big that box would be. The volume of that box is 27 cubic centimeters. So that's a pretty small box, right? Something like this, like that. Well, I guess you can't see height with this camera. Anyway, so the error that we have is smaller than the volume of that box. So I don't know, the box that's 50 by 20 by 15, it might be a box might hold a snow globe or something like that. And so the error that you have in measuring the volume is the error of that smaller box, less than the volume of that smaller box. So it's not too bad. Again, it depends on context. If you're looking for more accurate measurements, maybe you need a better tool. Okay, the second example involves waffle cones. So a waffle cone, to make a waffle cone, you make a thin waffle, and then you roll it into a cone shape while it's still warm, and then you wait for it to cool. You have your waffle cone. And in this problem, we're going to find out how much waffle we need to make a particular waffle cone. Now, some simplifications are going to be made in the process, right? So we're assuming that our waffle cone has a diameter of 4 inches and a height of 7 inches, so it's a perfect cone. So there's a simplification there. And we're going to say that the cone is uniformly 1/8 of an inch thick, which if it's a waffle cone, that's definitely not going to be the case. But we're just going to assume that to make the problem easier so we don't have to deal with a waffle of different widths, right? So now I want to estimate the volume of the waffle. Well, in order to estimate the volume of the waffle, I need to know how to find the volume of a cone. You can go back to geometry. The volume of a cone is 1/3 pi r squared h. If I look in the problem, I'm told the diameter is 4 inches, so then the radius is 2 inches. The height is 7 inches, and both dr and dh are going to be the change in radius and height. This is the thickness of the cone. I'm assuming that to be 1/8 of an inch. All of our numbers are in inches, so I don't have to worry about changing units anywhere. Now I need to calculate the differential. What is dV? So in order to do that, I'm going to need partial derivatives. The partial derivative of the volume with respect to the radius is 2/3 pi r h. Partial derivative with respect to h is 1/3 pi r squared. And we can write our differential, right? So there's everything with the partial derivatives plugged in. Now all I need to do is plug in the actual numbers that we have from the problem. So r is 2, h is 7, dr and dh are both 1/8. So I plug those numbers, and now it's just a matter of calculating. Pi over 3 cubic inches. So that's the volume of the actual waffle itself if we make these simplifications. Now, one thing to consider is if we have this cone that's made out of a waffle, so it has some thickness. We actually have two cones, right? We have if we measure from the inside and take the measurements of that cone, or if we measure from the outside and we take the measurements of that cone. So it might be important. In this case, we weren't told what to do, but we should figure out what did we do. If we assume that the radius is 2 and the height is 7, was that the radius of the inner cone measuring the cone from the inside, or was that the measure of the outer cone measuring from the outside? And if we assume that dr dh is positive, then these are the measurements of the inner cone. So we're measuring the cone from the inside. So from the inner edge to the inner edge, the diameter was 4 inches rather than from the outer edge to the outer edge. So we're assuming that these measurements are the inner cone, and then dr dh says we're moving outward 1/8 of an inch everywhere. And so that's how we get the change in volume. If we had assumed that these were the measurements of the outer cone, we would have had to have made this negative 1/8, which would have given us the same answer. It just would have been negative. So I guess in this case it doesn't matter too much. These are approximations. For an accurate measurement, right, they would be different depending on where we started. But again, this is just a simplification to illustrate how differentials might be used. All right, so that's it for section 14.6. Next, we're going to be moving on to a section in chapter 16, and we're going to be dealing with line integrals once again. We'll get to that shortly.